And we're rolling. All right, everyone. So, rocky planets. So this is why I do this class after we did exoplanets, because if I talk about the rocky planets, or if I give you all the class that I had when I was basically taking this class, these were all the rocky planets we knew about. And so everything we've learned, everything we theorized of what other planets should look like was based on these four, and maybe the little pebbles that are strewn around our solar system. But if we start with exoplanets like we did last week, and we say, well, we're seeing lots of big Earths, small Earth-like sized things, we're seeing the same densities. These things are pretty common. They're not super rare. They're not super special. By the way, if you need any help with this class, there are people at the Reach Center that can help you with this class if you're having any trouble with homework or anything like that. If you're really struggling, please come talk to me. The rule from the beginning of the semester still holds. If your semester is exploding one way or another, please come talk to me. We'll figure something out. There's also the Physics Learning Center, and that is also available for you. That has graduate students who are majoring in astrophysics to help you with this stuff. Okay, so I like the cartoons from XKCD, as you may have noticed at this point. And so this is the distance from me and the diameter. Basically, can I see them? And so here's the Earth. The distance from me is exactly the radius of the Earth. I've got the moon. I've got all the planets we can see at night. And really, anything that is smaller than that is going to be asteroids and comets, so they're barely planets. Planets ruled out because I would have noticed them above my house. Planets are ruled out because we would see them through the day. Planets ruled out because of the WISE survey, so the actual survey that we've done. Planets ruled out because we would be inside them, right? So there's a couple of things. The planet is so big that we would be inside the planet. The planet would be so big we would see it with our telescopes. But there is actually a small section, 10,000 AU or further away, planet 9 or dwarf planets. There is still some space left where we could have a ninth planet beyond Pluto, and we're actually searching for that at the moment, right? This is there's a little bit of a hint in the orbit of Pluto that there could be a ninth planet beyond that point. So we remember all Kepler's 3's laws when we talked about gravity. Planets orbit on ellipses. They sweep out the same area in a given amount of time during their orbit. So it's a very elliptical orbit. They sweep out. They go fast here and slow there. And the period goes as the major axis cubed, right? So these are things that hold in the exoplanets as well. And then we look at our the inner solar system. Mercury, Venus, Earth, Mars. So these are the guys that are going to be talking about today. And I'm talking eccentricity, and that eccentricity is very low. Only Mercury has a noticeable eccentricity in their orbit. So when originally people thought these things were on circular orbits, they weren't that wrong. And so we'll talk about the rocky planets and how they get heated and what happens in the inner solar system. And there's a kind of a logical divide. We saw this when we did the first sort of views with the planetarium, because you've got the three rocky planets here in the center, and then you've got the asteroid belt, and then you get Jupiter, Saturn, Uranus, and Neptune, and those are different clusters of the gas giants. And if you can then go even bigger, then you're talking like the Oort cloud. So this is objects that we haven't even detected yet, but we're seeing the very first ones. Sorry, if we shrink that down, we get Sednan. So this is one of the first things that one of those outer solar system objects, trans-Neptunian objects, TNOs as they're called. And we're finding more of those as our telescopes get more powerful, and we think there's basically a cloud of these things as sort of the border of our solar system. But they're all in the deep cold. They're all like dirty snowballs. So they don't reflect much light. The sun isn't very bright there, so we don't see. We need a very bright telescope, very good telescope to see that. So the thing about the solar system is that I'm sort of treading on what not quite astronomy, right? We can, I'm sort of posing as a geologist a little bit. So the intersection between astronomy and geology would be planetary science. The neat thing about our solar system is that we could go there. It's technologically possible. I'm not saying it's technologically easy, but at least it's possible. And so we can send a robot to various places, and so one of the first real how would I say, success stories here is Voyager 1 and Voyager 2. Pioneer is one of the first ones that managed to get to the outer solar system, and Voyager 1 and 2 happened because of an undergraduate project. An undergraduate project, it was an undergrad that went up to their professor and said, I would like to do a summer project with you. And as is then common, the professor panicked because he didn't have anything in his back pocket that he could give this person to do. So blurted out, hey, when is a good alignment for the outer planets for an actual flyby using, this is before, like this is, so we're here in the 1970s, where Pioneer has just managed to get to Jupiter. So when is a good position of all the outer planets for a flyby of all four? Now, remember, as the further out we go, the longer those orbits get, right? So for all of them to neatly align, this is very much like this person's being given busy work. You're going to come up with an answer, and it'll be 3 centuries in the future, and that'll be your summer project, and we're done, right? So we can just write it up and say, like, yeah, 3 centuries from now, there'll be a great alignment, and we should probably send a probe then. And the answer was 3 years from now. And so in uncharacteristic speed, NASA actually managed to put, together with academia, 2 probes together, these Voyager 1 and Voyager 2 probes. Because if you launch them, they can actually hook past every major planet and get pictures of them. But launching a major mission in a couple of years is, let's just say, unusual. So they managed to launch these in 1976 and 1977, and they managed to go past, like you can see, Voyager 1 went past Jupiter and Saturn, and Voyager 2 managed to catch all 4, sorry. And so later our rockets get better, and so we actually managed to get to some of these dedicated, like go to Cassini, for example, goes to the Saturn predominantly, but basically hooks past Jupiter to get there. And then otherwise we have these big missions. So we get a big mission every 5 years, 10 years or so. This is a big decision for NASA to do, right? It takes a decade or more to prepare something like this. It takes many proposals. So I'm not just going to talk about how we know what we know about these planets, but also how we got to know these things. For example, there was a space race. Yes, maybe this all happened before most of you were born. I mean, this ended when I was in middle school, so I'm pretty sure none of you were sort of looking at the room. I know that most of you weren't alive during the Cold War, and good on you. But what happened was that there was sort of a space race, and this is a sort of technological, I'm better than you, sort of keeping up with the Joneses. So between the USSR and the United States, and I would argue that lately we are entering a new space race. I'm hoping that this got recorded. Okay, yeah. So what you can see here is the number of missions sent to the inner solar system. So you got Mercury, who got a whole 2. You got Venus, which is a fair number. You got the moon, which is dominant, and I haven't updated this recently, but by now both China and India and private companies have landed on the moon. So you should think of that, maybe not all of you play Civilization, maybe some of you play other computer games, but there is literally a technological readiness level, a TRL. That's how NASA thinks. You have a level of technology that you can do. this is what you can do. So if you're in competition with another space agency, they go, we've managed how to land on the moon safely. That is a technological level. We've gotten to here. We've leveled up. There's a little gold coin circling over our head, or whatever. Right? So a lot of these are, for example, the Apollo missions. The initial preparations for that. The USSR was better at robotic missions. The NASA was slightly better at the human space flight. They sort of overtook going to the moon. But going to the moon already is tricky. There's enough of a delay that remote landing is hard because there's a 2-second delay. If you've ever played a video game with a 2-second ping, you've probably got blasted or whatever, because by the time you did this, the thing was already broken. It's very hard to drive or play anything that has that much of a delay. So you have to either be there or your robot has to have a good pre-programmed way to do it. But the moon is the easiest place to get, so now we have an Indian lander, and now we have a Chinese lander. And that was this is how you know that the Chinese Space Agency has some push behind it. It does help that you know that it's possible, right? Somebody else has already done it. It gets a lot easier when you can literally look at the picture of somebody else's rover. You go like, 6 wheels is probably good. You'll see, and even if you're not cribbing the notes, because I'm not saying that, right? If you know it's possible and you are a decent engineer, you probably are going to end up with a similar looking solution. And then you got Mars, and Mars eats probes for breakfast, dinner, and lunch, because it is the hardest place to land on the solar system. It's also one of the more interesting places to go. Typically, the success rate for a Mars probe was 50%, meaning that you had a coin flip whether or not you were going to get something out of it, and it takes 9 months to get there. So it can be a very disappointing year if you're part of the Mars probe. The reason that it's so hard to land on Mars is because it has just enough of an atmosphere that you can't ignore it, right? You can ignore while you're landing on the moon, you don't have to worry about its atmosphere. While you're landing on Venus, there is such a thick atmosphere that you can use a parachute, and it can even be not a great parachute, and don't worry, you'll stop, right? You can use a heat shield. Mars is just in between. There's enough of an atmosphere that you can't completely ignore it, but it's thin enough that you can use it to slow down or use a heat shield effectively. So you need to use a heat shield and a parachute and. So you need 3 things to work, not a heat shield or just a parachute or something. So Mars ended up being quite the trick, but then I want you to notice that the outer solar system has very few missions going to it. It's hard to get there. It's far away. And by inference, it's actually very tricky to send something and have it work the whole time and power it the whole time. Power is always the issue. If you go to Mars, Mars is sort of right at the limit where your solar cells work. If you go beyond this point, you need something called an RTG, a radioisotope thermal generator. You're basically using the heat from something that's super radioactive, which makes the whole probe already interesting to deal with. But you use the heat from radioactive decay in order to power your probe. That's what's currently powering the Voyagers, and still powering the Voyagers. And this is why they're Drew's favorite probes, because they're still going. They're now reaching 50, and they're still going. We get a whole byte worth of information from them once in a while. Not a megabyte, not a kilobyte, 1 byte, which is 8 bits. And it basically goes beep on here, but also it gives you an update of the actual instrumentation that's still working. They've reprogrammed the probes mid-flight. They've managed to keep them going. They still do science, even though they've left the solar system and left our in the outer solar system. So just to give you an idea, there are many missions from many different space agencies in different places. So we are now in a point where we're also restarting the Venus mission. So the next big mission is going to be to Venus, probably a double header, meaning that there is both a lander and something that's going to float in the atmosphere, as well as something that's going to orbit. As you can imagine, orbiting something is easier than, because, I mean, it's still hard to actually insert into an orbit, but that's easier than inserting to an orbit and then landing on the thing. So you sort of slice it up into different technological readiness levels, and there's sort of a running joke for NASA technological readiness levels that you start with, like, I thought of a unicorn, I put a stick on a horse, I launched the horse into space, it didn't die, it's now technological, unicorns are the reality, right? So this is the sort of the level that you can try different levels, and only when you're convinced that it works in space, literally you've tried it already, it becomes the highest level. So the terrestrial planets are the four innermost ones: Mercury, Venus, Earth, and Mars. And they're characterized by rocks, right? They have mostly silicate and metal, and they have solid surfaces. You can stand on the surface. Whether or not you want to is the second proposition, but all of these have surfaces that I can stand on. So this is the rocky planets, and then we have gas planets that do maybe have a surface, but it's very hard to tell. And so they have these characteristics. They're small, rocky, very close to the sun, have few moons or none at all, and they have no rings. Now, this is the kind of thing where if you start classifying planets and you only have our solar system to go on, then you come up with a class called rocky planets, and these are the characteristics. But it's going to be very interesting to see longer term if this class holds. Maybe we'll come up across with rocky planets that have rings, for example, or one of them at least has a very large moon. Mercury, for example, has no moon at all, but it looks like our moon. So it's very heavily cratered, and it used to, it is mostly locked into, it has a tidal lock where the rotation period is 2/3 of the orbital one. So it has a resonance with its orbital period and its rotating period are locked. So one day is every 2 Mercurian years, but it's a very short, it's close to the sun. There was a Mercury transit a few years back. That's fun. You actually see the little dot go across the front of the sun. But this is what it looks like. It is old, right? So one of the ways that you can sort of date material is that surfaces of nearby objects is how many craters does it have? How often has this thing been hit by asteroids and rocks floating in our solar system? And this means that Mercury is very, very old, because you started with a smooth surface as right after it is formed, and then you've just been smacking it with rocks ever since, and all those craters are still there because it has no atmosphere to smooth it out. It has no, I'm going to light it up a little bit because otherwise it's me talking in a nice, warm, dark room, and I know what that does to everybody, so I'm going to light it up a little bit. Yeah, somewhere in between. I'm trying to get the way that the slides don't wash out and you can all still see. And so yes, it looks very similar to our moon. Mariner 10 was now back in the 60s, the lunar-like surface. You can even see that with the DC telescope. Yeah, you can almost not tell the difference between the two, and actually Mercury is not that much bigger than the moon. If you then go to Venus, this is what you see. You see basically this smudge, this fuzzy picture, no matter how good your telescope is, because it has a very thick atmosphere. And so Venus was one of the places that has captured our imagination early on, because what's hiding under that cloud surface? Are there whole cities? Is this the smog of an industrial civilization that we haven't talked to yet? Or, this is, by the way, 19th century, think Jules Verne, right? This is sort of early 19th century speculation, because if you don't have radio, you don't know if anybody's there. And then the Venus Express, for example, radar mapped what the actual surface looked like. Lots of volcanoes, an absolute giant canyon, and so lots of evidence of geology, active geology, that resurfaced the surface a lot of times. But it is also incredibly dense cloud cover. And so Venus has, you can see the cloud cover change, but it is completely opaque. And so the Soviets, the USSR, managed to actually land a probe there, two of them. The Russian Venera spacecraft, or USSR's Venera spacecraft, one of them lasted all of 90 seconds, which was a technological accomplishment because the pressure is so high and the temperature is enough to melt lead. This is not, as you would say, good for robots to live in. Also, it rains acidic rain so bad that it so slowly dissolves. So this is the hardest place to actually put a robot and have it live for any length of time. So it landed, it went, ooh, I'm here, took a picture, and promptly died. So there's a reason that we haven't sent other robots there. It's just, nobody hates their robots that much, right? Yes, question?
Just out of curiosity, so you said that like Venus has like permanent cloud cover?
Yes.
Are there other planets that we know that are like the Earth in that they, you know, they have like some cloudy days, some days where they'll be,
We have 3 places in the solar system with a dense atmosphere. We're standing in one of them. Venus is denser than that and has permanent cloud cover. Titan also has permanent cloud cover. So permanent cloud cover is 2 out of 3.
So but they don't have like sunny days.
Right, a weather pattern, you need sort of in between. You need both liquid water, evaporated water, and condensing water. But so Venus does have different cloud layers and different cloud densities as well. So there is sort of a layer where it's more room temperature and room pressure. And there, for example, you would have a cloudless day and a cloudy day. There you would have weather more typical to us. But that's not on the surface. The surface is way below where it gets denser and hotter and acid rainier. So it just gets worse and worse. So one of the ideas is to actually have a balloon float in the atmosphere of Venus, and that way we can not have our robot dissolve and do longer term experiments in the Venetian atmosphere, because on the ground is just no good. Yeah?
Yeah.
Cool. Yeah. The rain is mostly sulfuric acid, which is if you know a chemist, that's the bottle to avoid. Think Drano. Yeah, friendly place, Venus. Also, it's very hot. But if you do then look at the composition, like you can actually see some lots of big volcanoes in this massive canyon. And so there is a lot of evidence that either it was geologically active or it is geologically active. So it has active resurfacing of its surface, which means that, because you can tell that because there aren't a lot of craters. If there were craters, they basically got paved over. And so we have our Earth-Moon system, and we keep thinking of our moon as normal, but it is not. It is a rather large moon for a terrestrial planet. So this is a gate that we may have to jump if a moon with all its tides is important for the development of life. And you can imagine, if you talk to a biologist, they go like, what's the most interesting, biologically speaking, environment? It's always the mangrove forest, the tide pools, like that, right on the coast where we get lots of tidal effects. It's like, really? So that's important? Yeah, they're most diverse. This is where, you know, you have sea life sort of interacting with land life and sort of changing over. Well, that means that this thing is super important for how life here developed. Here. Again, we only have the one example. But if that's true, maybe having a rocky planet isn't enough. Maybe you need a big moon on top of that. For all we know, that's true, but hey, maybe that's just our bias. And so this is except Pluto, but that's not even a planet anymore, and I know everybody's still mad about that. Every 4th, 5th grader, every 3rd grader is salty about it, and comes like, you weren't even born when they decided that, but no, they're still mad about it. I'll get to that next on Thursday. Now, The reason that we have this kind of atmosphere and we have so much liquid water is we have a certain amount of energy coming in from the sun, right? The sunlight, we have a certain budget coming in, and we then radiate it out in every direction. And if we measure the peak of the wavelength, basically the emission of the Earth, we notice that it peaks at about 10 micron. That is the equivalent of 255 Kelvin, or about 0 Fahrenheit. That's at the top, right? This is averaged over the whole planet. Sorry, if we, and then, but what about the surface? We don't have 0 Fahrenheit at the surface. It is considerably warmer there because our atmosphere holds the heat in. And this is called the greenhouse effect. And honestly, is there anyone in the room who hasn't heard the term greenhouse effect at this point in their lives? I'm genuinely curious because this keeps coming up. This is one of the most common things. So greenhouse effect. I'm explaining this, but every time I go through this class, I feel like I'm telling everybody something they've already heard, and I'll get to why I find that a little awkward in a minute. And so the greenhouse effect is when the atmosphere plays a role in keeping the heat into the planet. It makes it harder for the surface of the planet to radiate out its temperature. And so if you look at this temperature at the point of the satellite, right? If I look at that temperature, how much is coming in, and I would just have a billiard ball, and there would be no atmosphere. I would have for Venus, it would be 232 kelvins. For Earth, it would be 255 Kelvin. For Mars, it would be 210, because they're a little further away. Titan would be 82 Kelvin. But if I look at the surface, the Venus is 740 Kelvin. That's an oven setting, in case you're wondering. 288 for the Earth, 210 for Mars, and 94 for Titan. So, which one of the following of these four rocky things, Titan is the moon of Saturn, which one of these has no greenhouse effect? And you've got your voting cards, go dig them out. Voting in 1, voting in 2, and voting in 3. Yes, I see C all over. Fantastic. Yes, Mars is the same temperature as if it was a bowling ball, because it doesn't have enough atmosphere to actually affect the temperature of the surface. Right? So which one of these has the strongest greenhouse effect? Where is the effect the greatest? Voting in 1, voting in 2, and voting in 3. Seeing Venus all around. It is the largest temperature difference. Venus has what is called a runaway greenhouse effect, because if you heat a rocky planet, everything will outgas. Like you get more clouds, you get more, you get a denser atmosphere because everything that evaporates on the surface. So you end that denser atmosphere is then better at keeping the heat in. Now, our atmosphere isn't equally good at keeping the heat in at all wavelengths. It's pretty transparent in radio. It's not terribly transparent in the infrared because there's all these water clouds. And water vapor, and especially, is very good at blocking infrared radiation from going from the surface up and from the space into our atmosphere. Visible light is nice and transparent. We know that because we can see the stars at night and the sun during the day. Ultraviolet, nicely blocked. Thank you, ozone, because hey, otherwise we would have to slather ourselves in sunscreen all the time. X-rays, thank God that also gets stopped, because one X-ray is fine. Daily X-rays is not doctor recommended. Any doctor of philosophy, they all go, probably shouldn't do that. Gamma rays, same thing. So really energetic stuff that would give us cancer is stopped. And stuff that we can see by, not an accident, because hey, we developed here on Earth, but visible light is all visible. And so these are the molecules that are responsible for that, right? So this is how well does this molecule block the light, right? So I've got CH4. Anybody tell me what that is?
Ammonia.
Sorry, can you repeat that?
Ammonia.
Ammonia. CH4 is methane. also known as camping gas, or if you are not a purist, the thing that you use in your barbecue. That, remember the little canisters, that stuff that sloshes in there? That's methane. If you want to have a more visual one of that, it's also cow farts, right? It is the stuff that comes, it's a burnable material. I'm not going to encourage you to set cow farts on fire, but you can. And it is essentially natural gas of any kind of nature. I think I'm now done talking about cow farts because I didn't even get a single laugh out of that one. So, all right. NO2 is nitrous oxide. No one? Nitrous oxide? Laughing gas? Whippets? Am I that old? All right, I'm that old. But so this is the stuff that you have in the little containers if you have like a whipped cream dispenser, for example. That is laughing gas, also used sometimes at the dentist, but they have done something less fun these days. Oxygen and ozone, CO2 is carbon dioxide, and then H2O are well-known water. So how good is each of them at blocking stuff? And so you can see that, for example, oxygen 3 here, this is the short wavelengths, this is the ultraviolet on the left here, long wave, this is far infrared on here, and somewhere here in between is where our eyes work. And so this block here for the whole atmosphere, if you combine all these things together, our atmosphere is mostly blocked here by basically ozone. And then you've got all these blocking points here, and most of them are from water vapor, some of them are from carbon dioxide, nitrous dioxide, and then you've got methane in these two peaks here. Do you understand the graph now? Looking at nods throughout the room. Okay. So I have a question. Which molecules are added to the atmosphere by combustion? If I combust something, what do I typically add? Do I add nitrous oxide? Do I use add carbon dioxide, water, or D, all of those three combined? Voting in 1, voting in 2, and voting in 3. A, I got B, I got D's. Okay. I'm going to walk around. You're going to turn to your neighbor, and even if the two of you agree, explain to them why you chose this answer. Explain to them why you're right. You've got about 90 seconds. All right, let's vote again. 1, 2, 3. Definitely convinced each other. I see majority B and a minority of D, and a few A. Okay. If you're combusting something, you're burning something. So, for example, you take methane, which was our camping gas, right? Our barbecue runs off. So I'm burning that. What is burning other than combining it with oxygen? That is really what burning something is. Combustion, according to chemists, is literally take anything, add oxygen to it. You can do explosive combustion, but let's not go there. This is just slow combustion. I want to have a cooking fire, I want to have a camping fire, I'm cooking on gas, I'm doing something like that. So if I add oxygen, I'm removing some of this, and I'm adding that to either carbon molecules, so I'm adding CO2, or hydrogen molecules, so I'm adding water. You can see this, you have seen this winter. If you sat behind somebody in traffic, you saw the little white plume coming out of their exhaust, right? If it's cold, it looks like the car in front of it is making little clouds for a minute. Yeah, I've seen one person nodding emphatically. Is he doing this for everybody, or? Okay, You've seen planes go over with that little white contrail. That's water vapor condensing out into a little cloud. So if you burn something, oh, and you've seen this happen all the time, like you have a car in front of you, look at the tailpipe, it's dripping, isn't it? You've seen that part. This is water. The water is coming from the combustion. So if I combust something, I have two products, carbon dioxide and water. If everything goes well, by the way. If I have a 30-year-old car, all their stuff comes out, and please don't talk to a cardiologist about it because they'll blanch, right? This is the worst stuff that comes out. This is where you get asthma from, but everything runs smoothly, everything runs perfectly. If I just burn my camping gas, I get these two things. I get carbon dioxide and water. Those are the main products. So combustion does these two things. If I also, because there's nitrous in the atmosphere, and I'm busy combining things because it's a hot flame, and I'm busy combining things with nitrogen, and then you get nitrous oxide as well. So these are typically the three things that should come out of your tailpipe. If everything works great, and you've got a catalyzer that works great, and your engine is nicely tuned, that's what comes out. No soot, no smoke, just these three things. Is that something you had in science class at all? No? Because everybody forgets about water. Because water is benign, right? Water's fine. Nobody really dies of too much water. Well, okay, sometimes they die of too much water, but most of the time we're fine. The thing is, if suppose you're at high altitude and you're burning a jet fuel, you're getting both CO2 and water. That water vapor is immensely good at blocking infrared. So water vapor is a greenhouse gas. So is CO2. It's very good at blocking here at these two. Like this bump here is all CO2 all the time. Actually, methane is good at blocking in the infrared as well. So where do I block it? Do I block it at high altitude? That means the Earth is having a hard time with it getting the heat out. If I block it at low altitude, it's fine. It just has to get through that first bit of altitude. So maybe even a mountain can radiate it out. So where you put this, it matters. Okay. So you have heat coming in from the solar energy. Some of that gets reflected. There's a high altitude cloud. It's white. It reflects it right back out of the atmosphere. Or it gets all the way down to the surface. It heats up the pavement, right? If you've been on a hot summer day, do not walk barefoot on pavement, ever. And some of it gets reflected because it's like there's a snowy cap or something like that, so it gets reflected as well. It tries to go through the atmosphere, or it gets radiated by the atmosphere, so this is the atmosphere, this is the surface trying to radiate it through the atmosphere. Most of it gets absorbed and basically cycles through, gets reflected back into the surface and try to leave. So some of that gets through and leaves. And then the atmosphere also radiates on its own. So if I change the composition of my atmosphere, I get the ratios here start to change. That's what the greenhouse effect is. It's the same idea that if you have a greenhouse and I'm putting a glass panel there, I can actually have sunlight come in, but it's harder for the plants or the ground to radiate the heat away, so you actually stay above freezing. So I can keep growing my veggies for longer. That's just a trick. But if we do it on scale, if we do that here on the whole planet, we end up changing how well the atmosphere, the surface of the Earth can get rid of this heat. So what happens if one of these molecules is added in bulk? If I add lots of ozone, well, this was already not transparent. It's just going to be even less transparent. So even less UVs come through. I don't even have to worry. Sunscreen sales plummet. That's fine. If I add lots of combustion, I get more of these peaks blocking light coming off the surface, so I make the surface hotter. I make the surface warmer. So that's what the global warming is. If I shift the balance of the composition of the atmosphere more towards CO2 and then also water vapor. So yeah, this is the CO2 content of our atmosphere. We've passed 400 parts per million a while ago. And so this is from the National Ocean and Atmospheric Administration. So this is the people that literally do your weather. And if you look at a weather app, this is where their original data come from. They operate the weather satellites, and they keep this stuff, they keep track of these things. And this is measured on top of Mauna Kea. There's no industrial plant nearby. You want to have this, you want to have an average, so you don't put this right next to a smokestack, because otherwise you would skew your measurements. And this feels like, who has seen this particular kind of plot before? Few of you. This is the increase of CO2 in our atmosphere. I have a couple of questions for you. And so this is over the last decade. So why would this fluctuate like that? Why would it go up and down like that? Any ideas? Oh, come on. What is CO2 good for? What eats CO2? Plants eat CO2. So could that be, yes?
I would say, would it be the change of seasons?
It's the changes of seasons, because it happens twice a year. This whole loop is 1 year. So if we have the northern hemisphere has way more land mass. So we have the summer in the northern hemisphere, we're all growing our crops, we're all growing our trees. It's absorbing all the CO2. This is literally all the plants in the northern hemisphere eat this much CO2. So if you go like, maybe you should plant more trees, I'm with you on that, but that's, on a given year, that's the amount of the difference it makes. So this isn't the atmosphere, this isn't the plants breathing out the CO2. We can see that, right? It's breathe in, breathe out effect. And here we have the global average temperature. So annually, it goes up and down quite a bit. So if we actually smooth this is 5-year mean. So take an average over each 5 years. Each point is the 5 years on either side. And then you see that it actually keeps increasing as well. However, it's in Celsius, and none of us here, except me, do Celsius. So I'll see if I can get the Fahrenheit one there as well. However, I've also seen this plot. And again, this is a science class, so I want you to be skeptical when a plot is presented to you without further comment. And I've seen this, and somebody has said, look, it goes up, it goes down, I don't see any difference. This is from the 1950s to the 1980s. There is no global warming. Same data. How did I lie to you here? I've been lying to my teeth with this particular plot. How did I do that? That's a good thing to be aware of whenever data gets presented to you. You can lie with data just as hard as you can do with words. How did I lie to you here? Yes, sir?
Does that have to do with the y-axis?
Have I messed with this?
Just like the framing of it?
I mean, look at how small these variations are. It's almost as much up as it is down. This is the real data. What have I done? It's something really insidious and sneaky. Yes?
The line that you drew through it? Does that have to do with the line that you drew through it not being?
Have I drawn like a suggestive line? That's always a good one, but yeah. I've measured in January, which this goes from January to January 1950 to January 1960. This is the 10 years, the average temperature in between. This is a very simple but also very sneaky trick to lie to people. It's in the premise, yes.
Is it because it's in Celsius?
Nope, Celsius is a perfectly good measure for everybody, including Canadians, use it. So I think half the time. Canadians are weird. They measure their weight in stone, but their sugar in kilograms. It's confusing. Yes? Lacking context is a good one. I'll go back to where I got it from. This plot starts in 1880 and goes to basically now. I have picked exactly this bit here so that it doesn't look like it has changed much. Oh, sorry, this bit here. I went with like local peak and local minima and actually put those on either side. I picked the y-axis and presented it as if that was all the data that was available. I'm sorry, did we all stop using thermometers in 1982? No, there's data. There's tons of data since. There's 4 decades worth of data since then. Right, so the trick here is that if I pick the right window, I can, and then pretend that that's all the data there is, I can sell you on this, right? So whenever, this is something I do in my 275, like scientific plotting course as well. If somebody presents you data and they just pretend that that's all the data there is, you have to go like, so why exactly did you start at that year and why exactly did you stop at that year? Were those 2 convenient years for you? Did you just window this out to something that proves your argument or proves something that you want to show? You can always lie with data. I haven't changed a single point. Yes, they were in Celsius, but that's the measurement. Were these by in January? Sure, but you know what? That was fine. I just windowed it down to where I can lie with it. So I want you to be careful whenever somebody presents you data, including me, including other people. Sometimes people do this inadvertently, but they go, all right, here's all the data. Why do I start? So let's do that exercise here. Why do I start in 1880 here and not earlier or later? What do we remember about 1880? None of us remember anything about 1880. We weren't around. The Industrial Revolution happened. So we finally had standardized, mass-produced thermometers. So every post office, every naval station, every, you name it, had a thermometer and logged it. So suddenly we go from one geezer in England has a thermometer that he invented, so it's very hard to tell if he's actually got it right or not, to everyone has a thermometer and logged it into their diaries and logbooks and ship's log and what have you. So suddenly we have an explosion of data here, so we can actually get an average temperature. That's a reasonable reason to start in 1880, right? Rather than, let's say, 1863 or something like that. Why did I stop here in 2020? I haven't updated my slides, I'm sorry. That's it, but that's a fair reason. So we see a trend going up. We saw the trend going up with CO2, we saw the trend going up with temperature. So if I take now a model for the whole atmosphere, this is something we're interested in, right? We want to see long-term predictions for, so we have the historical scenario, we have a US Geological Survey's temperatures, and we actually want to model these. As we go along, 0 degrees change 1, 2, 3, 4, 5, 6. And now we model this all the way to the end of this century. If we do that, we're going to end up with 5 degrees Celsius, which is about, I think, close to 10 degrees Fahrenheit difference on a global temperature scale. This is the part where everyone goes, oh, this is a problem. And you don't even have to be a goat herding hippie to think this is a problem. If you are an agriculturist, you're a problem. If you have a power plant that needs cooling, it's a problem. If you don't like your AC bill now, it's a problem, right? So this is a thing that we have to worry about. This is sort of the same thing, but this is the actual measurements till about 2016. I like this graph because it shows that at the end of, right where we start with the Industrial Revolution, it is actually not that noticeable yet. But a lot of the carbon dioxide it put in the atmosphere was really in this latter half of the 20th century, so you can really start seeing that effect. We're getting very close to that 1.5 Celsius, which is the limit that the International panel on climate change has sort of put the like, yeah, this is where things get really weird and bad and unpredictable beyond that 1.5. It's not just the size of the change, it's also the speed of the change. So another thing is like for centuries and literally millennia, yes, temperatures have changed. We know so because there used to be ice ages, and those ice ages literally poured giant glaciers through northern Europe and here, right? We know that because they left rocks behind. So there was an ice age. Humans lived through it just fine, but they also adapted, right? Not only did we wear the woolly mammoth, but our skin got lighter, and we absorbed more light that way for vitamin D production. So, but you can see that this is the changes over time. This is very, very fast. Now you're going to go, okay, you just taught us about that x-axis, right? This is the CO2, this parts per million, and it changes over time. And yeah, okay, went over the 1950 level just there. I'm sorry, did you have a scientist for over the last 400,000 years carefully measuring CO2 levels that we didn't know about? Some 400,000 years before the Industrial Revolution? How did you do that trick, right? This is where you become my fellow skeptical scientist. You go like, where does this data come from? And the reason is, no we didn't, but the Earth itself has kept a record in the form of cores in the ice in Antarctica. So if you drill down in the ice in Antarctica, Antarctica is a desert. You see that it has all this snow and ice, and you go, oh, it must be snowing a lot there in Antarctica. It does not. It is a desert. It's very, very dry. But every time it puts another layer, it doesn't evaporate, melt, or anything. So basically it adds layer after layer very slowly. And so if you drill down in the ice, all of which is basically compressed snow, there's little bubbles of air, so you can measure the CO2 content every layer as you go down. And so as long as you figured out what the last few layers told you, where you have temperature measurements for, and local measurements for, then you can figure out what the rest tells you what each year is. The jumps here are a little bigger because an inch is a millennium and not 5 years. So you can figure this out. So you get a much longer baseline. You get like, this is what the Earth normally does. There's a fair bit of variation. We've had tropical times, we've had ice ages. This comes and goes. This is actually quite normal for our Earth. That's good to know. This isn't normal. It has been several billion years that it was ever at this level. And that was before trees were invented by nature. And when trees happened, the CO2 dropped below this level. So it's not just the amount, it is also the speed. And so now we want to predict the future because, well, if this is going to get hotter, where do I put my farm that I want to retire on? And so you look at the continental United States and go like, where is it going to get hotter? And what should I plant there? Should I plant corn or something that's a little more heat resistant? And so here in Kentucky, for example, this is 1950, this is the, a few years from now, it is on average hotter, and it's also on average drier. So whatever you do here, we're already switched over from tobacco, so we can switch over to something else. But keep that in mind if you're having like an agricultural product. So why would this be so difficult to predict? If I do the whole globe, okay, because I'm adding it all over the globe and the average goes up a little bit, sure. But we've had places that the average actually locally went down, other places that go way hotter than that. Why is this so hard to predict? This is the participation class. There's another one on Thursday, sorry. Why would this be so hard to do? Yes?
New companies formed,
Pardon?
new hackers and stuff like
There's new places. China just entered the middle class in less than a decade. It's the kind of thing where like everybody owns a car now. Every family is very proud of their new car. So yes, suddenly we have a whole bunch of CO2 coming out of China. What else would be hard to do? It's weather. It's hard to predict this afternoon, right? It swirls, it changes. Just a tiny change in the jet stream means that weather pattern actually doesn't go to California than it goes to Oregon, right? So having tiny changes make big differences later makes climate on longer timescales very tricky to predict. It's hard to say if cloud, so there was a whole discussion, are clouds good or bad? Clouds reflect light, right? It's a big white fluffy thing. It reflects the light back into the, doesn't actually manage to get down. Like it covers the earth and reflects it out into space. That's good, right? But also they reflect on the bottom side, so they reflect things back to earth. So where do I put my cloud? If I put my cloud really high up, it's actually keeping the heat into the atmosphere. But if I put my cloud low down, it's reflecting things back into space. So where do I put my cloud? How dense is it? So for example, plane contrails are bad. They're at high altitude. How do we know this? Well, you've all grown up hearing about 9/11. It was a week of no plane travel at all over the continental United States. None. There's usually something like 500 flights at any given time in the air. So there was no point of a scientist going, all right, just for shits and giggles, can we stop air travel for a week? I want to check something. Yeah, that's never going to happen, except that it did. So we had an artificial experiment of what happens if we have no air travel over the continental United States. It's 3 degrees Fahrenheit cooler if we don't have those contrails, because they keep heat in. Oh, so clouds up high are bad, clouds down low are good on balance. How important is the jet stream? How important are the flows in the ocean currents, for example? What happens if I melt ice? This is a question for that you get, I think, in a Google interview. If ice cubes melt, the water level goes up, goes down, stays the same. I'm in Europe, there's no ice in my glass. Volume 1, volume 2, volume 3. I got A, C, and B. All right, I think I got majority A. Goes up, goes down. So the volume of ice, it's the weight of the ice cube is, that volume is displaced, so it's the same amount of weight as the volume that you displace. So the volume that's displaced is the same as the weight for the water for the ice cube. So if you melt it, it actually stays the same. It stays close to the same. So if I melt all the icebergs, there isn't really that much of a change. There's a little bit. But this ice is on land, Greenland, recently in the news, Antarctica, not so much in the news, but if you melt the ice on those, then it's running off into the ocean, and that means the ocean is increasing. Not only that, I'm heating up the water of the whole ocean as it is, and so it expands. You know, if you heat something, it expands. So that's what if you look at a pool at the end of summer, it is at a higher level. It doesn't mean that all the little kitties peed in it, maybe, but it's mostly that the water had up and actually expanded. So you also then get this part, this whole chunk of land doesn't reflect heat anymore because it's no longer covered in ice. So now it's absorbing heat instead of reflecting. So there's a lot of things that sort of accelerate the process, to the point that when the first models came out, there was a moment with like, how are we not either a ball of ice or Venus? Because Venus is one runaway, and sort of Mars is another. How are we still, you know, sort of in that Goldilocks zone? How is this balancing out? It's because if all the processes work together, most of them sort of help correct one way or another. So if you are an ice age and you cover everything with ice, why doesn't the temperature drop more? Because you keep reflecting. Like, why does it not do a runaway one way or the other? And so why the higher global temperature linked to higher sea levels? Iceberg melt, land ice melts into the ocean, warmer water expands, B and C combine. Warmer oceans have different currents. What do you think it is? Volume 1, volume 2, volume 3. It's B&D combined, right? It's the warmer oceans also expand. So yeah, sea level rise. Here in Kentucky, not as much of a problem. If you happen to own real estate in Florida, a little bigger of a problem. If you come from a country that's already technically below sea level, it's a little bit more of a problem because we built all the dikes and levees and what have you in New Orleans and everywhere to about this level. And so if that level is now higher and we get a big storm, it now gets more dangerous. So in my data visualization class, one of the things I have them do is basically produce this plot. This is the same data. It's not connected, but I'm trying to show the same information multiple times. So I'm showing the global difference in temperature in Fahrenheit, in Celsius, and as a color. So that way, if you are somebody who's visually more attuned to color, you kind of go like, okay, it's also red is bad and blue is good. How our brains work. Our brains are odd that way. But this way you can say like, okay, here's normal, that's sort of white, and if I go up that, then it's red, and if it's below that, it's blue. If I'm here in the United States, I can see that it's 1.5 Fahrenheit. If I'm in Canada, I can sort of like, oh, it's almost close to a degree Celsius. This way, we reach all audiences. So this is my whole spiel there where I'm like, look, if you want to convey something to all audience, make it easy for them to read. Make it easy for everybody to understand. This is really, if you're going into science, if you're going into any science, make sure that you keep that in your mind, and not because you've read yourself in for a year, but make it easy for everybody to understand immediately. This is tricky, actually, so evaluates everybody's efforts accordingly. Now, that comes down to messaging. Has everyone seen the movie Don't Look Up? It's 2 people who hasn't seen the movie Don't Look Up. Come on, it was on planes for forever. And streaming, etc. And there was like, a very earnest 15-minute lecture by Leonardo DiCaprio, and does anybody's opinion actually change? And this is the part where I struggle with this class, because I always feel like I'm sort of blasting this information at all of you, and you all seem to sliding down your chair, trying to not be noticed. It's like, oh God, he's going to ask us questions. Does anybody's opinion actually change? And especially if you hear, so does lecturing actually change your mind? Before a Hollywood star gives you a private lecture on climate change, you are perfectly happy to drive a small Japanese pickup truck because the bed's just as big as the other one. And after a Hollywood star with a private jet lectures you on climate change, you kind of go like, I can run this thing on coal. So I understand that part, right, where somebody who's much better off than us does this lecturing from down high. And I want to avoid that here. And meanwhile, I realize I'm the sage on the stage, and I'm trying to avoid that as a system. This is why I want to get information from you. This is why I want to get your responses. And the reason for that is, somebody actually did their research. If you want to look it up, it's over here. The main thing is that, yeah, people do vote more like, this is a problem. Global warming is an issue, but it feels like such a big problem. And the messaging has in part been like, oh, we should all solve it, and you are responsible. This is the generational thing that I feel is the biggest problem here. Me, an older person, is telling you all, the younger generation, that this is a problem you should definitely go out and solve. And you go like, so what do you do? It's like, I gave you a lecture on that. Like, yeah, you should probably do a little bit more. So the assignment is, I don't want to be just lecturing at this. Gloom and doom is like, we can't change anything. Like, it's such a big problem. It's our whole Earth, right? I don't want to hear another dystopia where the entire world's on fire and robots have taken over, or mushrooms, or whatever. It's great TV, but honestly, it's a bit much. What does it look like for you when we get it right? I'd like to hear what that would look like. What that would look like in your life, in your commute, in your work, in going to school. Maybe you go like, look, I can't figure out what 10 years from now is going to look like. Pretend it's your parents' place, right? How does your parents' place look 10 years, 15 years, 20 years from now? where we got it right, because collectively we have done quite amazing things. That's the message that I really want to get across. That ozone layer, I've literally seen somebody say, you don't hear anybody about the ozone layer anymore, and that was a whole thing in the 80s and 90s. Yeah, we had an international treaty, and the treaty worked. Nobody made the stuff that broke down the ozone layer anymore, and the ozone layer repaired itself, and it's no longer a problem. Still not a great idea to have red hair in Australia because you're going to burn, but you're not going to instantly get skin cancer. It's got solved. I get nothing from the room. Is this something that you'd like to do? Absolutely, please write me like a small thing, like I think I'll be driving an electrical car, or I'll be driving a scooter. I'll be jetpacking to work. You know, something. I want to hear what your future vision is. It's like, hey, we solved it. It's going to look like this. I think that's a much better exercise than going, we should all feel bad. I've been in your seat, and we already were talking about it, and felt like I was being told, you should feel bad for burning. Like, I had to get here. So I'm curious what it looks like for you when we do get away. All right, I'm going to skip the group work for today, so I want to just talk about Mars, because Mars is so cool. This is what it looks like from Earth, and it totally tricked us, because there was an Italian astronomer at Lowell Observatory, who saw some stripy structures and called them, in Italian, canali, which is also a way to just say stripes. And that got mistranslated as canals, and oh my God, there are canals on Mars, there must be civilization, they're using those poles to irrigate their equator. This is fantastic. So Lowell built a giant telescope just to check out the Martians on Mars, which weren't there. And so once you get a look at it with the Hubble Space Telescope, you realize, like, yeah, this isn't vegetation, this is just darker surface. And you see, for example, these massive shield volcanoes and this enormous Valles Marineris is as big as the entire United States, so it's basically the Grand Canyon if it grows up to be a fully Grand Canyon. Martian days are about as long as our Earth, so that also makes it a little more hospitable. It starts to sound like it's like poles, it's got some weather, it's just missing an atmosphere. We're almost there. 24 hours, yeah, this looks great. But it's a very thin atmosphere, and so most of it is CO2. The ice caps are actually mostly CO2. It is dry ice. Anyone played with dry ice? Anyone had like the disco effect with like the clouds over the floor? That's dry ice. So it's mostly dry ice. It does look nice and white, but it is, and we are looking for water there, and there's definite evidence of water having happened. For example, this is definitely a river. You show this to a geologist and they go, riverbed, that's it, nothing else does that. Because this is the Ohio River, this is the river on Mars. So it's like, yeah, that looks like a riverbed. Where did all the water go? It's definitely a gully. This is what water does. And a lot of different things have shown that, yes, there is ice and it's sort of just below the surface. All of this makes us and certain billionaires extremely excited to go here. And it's fun to fantasize about it, right? But it's got the highest mountain in the solar system. We sort of had to define the sea level, so it's sort of the average height of but it stands 22 kilometers above that, so that's like twice Mount Everest. And since we haven't gotten a sample from Mars, we sort of have to make do with whatever has been knocked off Mars by a meteorite and then lands on Antarctica, because then these black rocks stick out like nobody's business in the white Arctic expanse. And so this was a little thing that they found in one of those. And it looks like something biological, but it's basically a calcite deposit. So it's good indirect evidence of liquid water. It's kind of terrible evidence for life there. And so this goes back to the Spider-Man hypothesis of grand claims. Great claims require great evidence, right? Grand claims, what is it? Power something, help me out here. great power requires great responsibility, right? So great claims require great evidence, and this isn't it. But we send probes there. This is the Viking. So again, talking about those technology levels, landing a little tripod somewhere, relatively easy, because it just has to land not on a rock. So some luck involved. If it had landed right on top of that, it may have just ended up on its side. That's why I said 2. But then you go like, yeah, but suppose you're here and you go like, oh man, there's a really interesting rock right there. And my little robot arm can't quite get to it. I've traveled, half the solar system. I can't get to the thing. So I need wheels. And so that was the next thing. That's the next, can I do something wheeled on Mars? And this toaster-shaped thing is one of the missions that we sent. And I want to actually see the family. Yeah, here's the family report. Here's the first one. This is Pathfinder. You've seen the movie The Martian. It plays a role there. This thing is the size of a microwave. It was just to see if we can design wheels that could work there. And really nothing else. The science was tacked on at the literally last minute, like, here, science instrument. There, go. Right? It's just to figure out if we could do it. JPL launched this thing, it bounced over the surface, and then folded out and send its little cart out. And just learning how to drive on Mars. This is the learner's permit card. And then Opportunity landed, and so now we're talking actual proper a proper rover with actual instruments on board, both Opportunity and gosh, now it's based on the other one. There's 2. Basically, we made twins, and they landed around. These were our first geologists on Mars. Go around, knock on some rocks, see what comes off, see what they're made of, and travel around. This Spirit, there's the other one. It takes, you kind of go like, you see this, and you think, they're almost doing wheelies and making a dust plume here on Mars, right? No, this is one day. It takes a while. Because it takes 45 minutes to send your signal and have it answer back. This is playing Mario Kart with the worst lag ever. So you're going here. Okay, figured it out. Okay, it's there. Okay, now we go here. So take it slow, because there's nobody nearby to write your little 6-wheeled trike if you flip it over. But there are people whose job, I love this, they have a bumper sticker, my other car's on Mars. That is just, if you work at JPL, that's fun. Here's another one of those things. They were solar powered, and NASA has officially ended the Opportunity mission because it ran out of power. But I want you to keep in mind that I talked about the Hubble Space Telescope mission, for example. There is if you last this long, our mission is a success. And with Opportunity and Spirit, this was, if you last for 90 days, we're considering you a success. They lasted 1.5 and 3 years, respectively. They just kept on trucking. This thing was almost indestructible, and the thing that killed it was the Martian dust. It just got so dusty that it wouldn't recharge properly. And so, yeah, it's like the battery is totally disconnected. How could this still be moving? Given what it did to the Mars 2020 rover, we may never know. Everything the light touches is our kingdom. What's that dark area? That's Opportunities, half the planet. We must not go there, right? It got a little spooky. And so this is the family portrait. That's Pathfinder. This is Opportunity and Spirit. So, sorry. I knew it was long. It was 6 years and 19 minus 4, 15 years. Not bad for a 90-day mission, right? So these things kept on trucking, again, because they were battery powered and solar panel powered. Eventually, and every year it sang its own birthday song, just to no one. And this is what we've got running around now. That's the size of the car. So I will end with this thing here. Yes. Why is this hard? This illustrates why Mars is hard. We send the rocket on its way, we boost this thing to its up to speed, and this is the actual lander plus everything. If you need to leave, that's okay. I'm just ending on the fun animation because essentially for 9 months this thing is just flying free. So it's not doing anything. You're just checking whether or not it's alive. And so the team just sits there for 9 months. I mean, you're checking the vital signs, etc. But there's nothing for you to do. And then once you get to Mars, you hopefully have inserted you into the right orbit, and you get, at some point you get rid of this like solar cell. So you get here 8.5 months later. You gotta be patient. You gotta have good nerves of steel because this is the part where it gets interesting. We now have about 50 minutes of terror because it's doing all this stuff on its own, right? Apologies. So it's doing all these things on its own because again, it's 20 minutes. So if I send a signal, it's like 20 minutes to get there and 20 minutes to go. I receive the signal. So there's no way to steer. There's nothing to do. So you have to send a completely autonomous robot. This was the first sort of autonomous robot sent by NASA anywhere. It landed, and so it has to do a bunch of different things in sequence. First, it has to get rid of the heat shield and the encapsulating. It has to land with the heat shield for a little bit to slow down some of the way, but because the atmosphere is not thick enough to slow you all the way, like the Apollo astronauts, for example, it also has to deploy a supersonic parachute. So anything that lands in our Earth, and has anyone seen the pictures of the astronauts coming back from the ISS in the water with the dolphins? I should go dig that out. It's so awesome to look. Like I saw that, it's like that's an album cover right there. But like you see the parachutes land, those are not supersonic, right? You do not deploy a parachute when you're still going faster than the local speed of sound. But for Mars, you never slow down enough to deploy a normal Earth parachute. So you have to design a special one that can do supersonic and go down to subsonic. So first you bleed off some speed with the heat shield, but the heat shield isn't enough to do all of it. You drop the heat shield at some point. I don't know where it does that. And it has to keep on track, so that's what these little rockets are for. No longer heat shield, drop all that stuff. So you drop a whole bunch of things before you even get to the ground. And you deploy that supersonic parachute. First parachute, and then the second parachute, and there goes the heat shield. So this is the part that sort of slows you down almost the rest of the way, but this is the one time. We're sending one of these things, so we want it to land not on a rock. And so the last bit is done by hovering on the rockets. Literally, it's called the sky crane. It hovers on the rockets, finds a good spot to land automatically. Again, we can't steer, this takes too long. And then you find like, okay, here's a good spot, we're gonna drop our rover here, and it does that on a little sort of rappels down. It all does this automatically and on its own. And so this was the first time we had an automated or sort of auto decision where to land. It sounds in the age of AI a little less of an issue, but remember that this was about a decade ago that this was designed. So it was the first time this autonomous vehicle was used. And so yeah, then it stays there, has the rockets burning while you gently lower the, I mean this is the size of a small car, drops it off, and then when it's done, it flies away so you don't drop on top of it. So then we have our lander on Mars. This thing, it has an RTG, so it has a lifetime of forever, as long as nothing breaks. If it breaks, it has the boom out. This is where the RTG sits, so yeah, notice no solar panels. This thing will last forever, and it has a whole suite of instruments on board. So we have like a fully robotic geologist on Mars now. And this is why we're learning more about Mars much faster. Trick is, if you put a random geology grad student in a spacesuit, he could do the same amount of science in an afternoon. Humans walk faster, they do geology faster. This basically slowly walks up to a rock, then there's a whole discussion whether or not we should tap the rock, etc. We have one go at this, right? The overruling thing is do not break the robot, because nobody's nearby can fix the robot. But yeah, this is our current robot on Mars, complete with the boom with the stereo camera, so we can actually see all around and check whatever is around. Plus, oh, sorry, this is the cameras. That's the like the whole panel of scientific instruments, including, of course, a giant freaking laser, because science isn't complete if you don't have a big laser beam to shoot at things. We can ablate stuff and drill into rocks, and we can actually see what these things are made of, and that is, that's what we want to do. We want to go up to a thing and knock it and see what's happening there. So yeah, we have a full lab on wheels on Mars. But this is the kind of thing, yeah, that's what you get if it takes a few $1 billion to build. This is hard. Everything was built to spec. We didn't build a second one, there's one. And so, yeah, welcome to the laser lab on Mars that can now drill and analyze everything that it sort of comes across. It is one of the best selfies ever, so it takes regular selfies of itself, and it's powered by the RTG. It's glowing because it's hot. It's a chunk of plutonium. And so you go like, hey, has anybody else done this trick? Yes, the Chinese have. So not as well advertised and doesn't come with this nice graphics as NASA, but this is the Chinese Mars rover seen on Mars. There are other people's rovers on there. This is a technology trick that the Chinese figured out fairly quickly. It looks very much like Spirit and Curiosity. Yeah, you end up with the same engineering solution whenever you do. So Mars is the only planet entirely populated by robots. I will leave you with that. I will see you on Thursday. Thank you for indulging me on ranting about Mars. I can do this for the entire semester, and this is why I leave it till now. So I'll see you on Thursday. Thank you.